So we looked at the case for delta G mixing if we have ideal mixing going on in our system. Let's look at the case where there are non-idealities in the mixing. Okay? So we have a non-ideal solution. Then our molar Gibbs energy, the total molar Gibbs energy, is going to be equal to the ideal solution term plus the entropy of mixing term plus the excess Gibbs energy. So if we take a look at delta G mix, for non-ideal mixing, we will have that entropy of mixing term and the excess Gibbs energy term left over. Okay. All right, and so now what we want to look at is, how will this excess Gibbs energy affect our delta G mix curve? Okay. And to at least demonstrate this, we're going to look at the case where our excess Gibbs energy is modeled by the single one parameter Margulies equation, which, if you remember from the previous videos, is just A, x1, x2, and this A term has a temperature dependence that could be modeled like this, where A is equal to some constant over RT. Alright? Okay, and so if we have a curve that looks like that, and so previously we saw in this delta G mixing curve, if we have the ideal mixing, we just get a parabola like that. But if we have an excess Gibbs energy contribution in our curve, and it's large enough, we'll see that the curve will evolve into this form, into this top curve right here, where it's not just a parabola anymore, but now it's like a parabola that has a bump in the middle. Okay? And so that bump is concave down as well. And so this bump, the appearance of this bump is important because, to determine if a, one-phase or a two-phase behavior is going to be stable, we have to look at, the shape of this delta G mixing curve. And so, for example, if we take a look at a delta G mixing curve that has this concave down bump, we can now look at a couple of different scenarios. All right? And so let's say that we had a solution that the overall composition of the solution was x1, right? And so that would be somewhere here. To determine if this x1 is stable, we have to look to see if it's possible for the system to have a lower delta G of mixing than the delta G of mixing at x1. And so we see here that for our delta G of mixing, for the value at x1, if we go to any other mole fraction value, we see that we actually decrease our delta G of mixing. Okay? And so if that's the case, if it's possible for us to decrease our delta G of mixing by going to another mole fraction value, then that would mean that this original mole fraction value here is not stable, and the system is going to want to evolve in such a way that it will decrease its delta G of mixing. All right? So we have a couple of possibilities. There's a whole range of x values that give a lower delta G of mixing than this original value. And so how can we determine, what the stable value is going to be? Well, to determine that, what we have to do is, find 2 points on the phase diagram and draw a line to connect those 2 points, like is done here. And essentially, in order for those mole fraction compositions to be stable, the line drawn between the 2 points can't pass through the original delta G of mixing curve. Or in other words, that line has to basically touch the lowest points in that curve. Okay? And so we see here that the line that's drawn here is always below the delta G of mixing curve. Okay? And so we call this line a binary tangent construction. And that's because the line only touches the curve at these two mole fraction values. Okay? And we have to remember that essentially what we're looking at here, the slopes here, because we have a straight line here, and the straight line only has one slope. And we see that at the points where this line touches, where the tangent line touches the curve, the delta G mixing curve, the slope here and the slope here are equal to one another. Okay? And essentially, if we're looking at the slope of a Gibbs energy with respect to composition, what we're looking at is the chemical potential. And so at these 2 points, essentially what we're saying is that the chemical potentials of the species 1 in the prime phase and species 1 in the double prime phase, those chemical potentials are equal to one another. Okay? And so that's the idea there. And so to kind of reiterate this and re-explain it in words, for situations where delta G mix has a concave down portion, there exists regions, or x1 alpha, there exists x1 values that are between this x1 alpha and x1 beta value, where delta G of mixing can be lowered by splitting or phase separating. Oops. Oh, I think it's going to be video notes. By splitting into 2 separate phases, where each of the phase, so the alpha phase has x1 mole fraction of x1 alpha, and the beta phase has a mole fraction of x1 beta. Okay? Alright, and so just to kind of sketch out that plot I just showed you, which is, for the first time seeing it, it's a kind of a complicated plot. And so I'm just going to kind of sketch this out again. Alright? So let's say the y-axis is delta G mix, x-axis is x1. And so let's say that, you made a solution that had an overall composition of x1 naught, I guess, right? But we could see that if you're at this composition, it's possible to lower the free energy of your system. And so the system will phase separate in such a way that it will form 2 phases, an alpha phase and a beta phase, where not only are the delta G's of mixing lower, but you also essentially minimize the chemical potentials. Okay? And so at these 2 points, the chemical potential of species 1 is the same. And so that's visualized by drawing that tangent line. Okay? And so slopes of delta G mix curve are equal at x1 alpha and x1 beta.